Welcome to Alaska Earthquake Science Facts. I'm Carl Tate. Alaska's environment, wind, rivers, permafrost, glaciers, sea ice, can be monitored using the faint signals of continuously moving ground recorded by seismometers. This is a photograph of Dr. Kyle Smith installing a seismometer in Minto Flats. This seismometer, shown here, recorded continuously for 4 years. And this fact is about some of the amazing and ordinary things that an amazing instrument can record. There's so much material in this topic that I had to split it up into 2 videos. And what I'm showing here are the takeaway topics for the background, the part A, which is the previous video in this playlist. And so here they are. A seismometer can record signals coming from close, like a moose walking next to it, and from far, like an earthquake on the other side of the planet. The Earth is continuously in motion, and this continuous motion or ambient noise provides information on many things besides earthquakes. The frequency domain offers a powerful tool for analyzing signals of ground motion, and the dominant signal of ambient noise, periods 5 to 8 seconds, is generated from the seafloor by the interaction of oceanic waves. So for this material, check out the previous video in the playlist, and we'll move forward with an understanding that we have some of these basic ideas. Here's 25 seconds of ground motion recorded in Minto Flats, Central Alaska. Here, ground motion could be displacement, the velocity or speed, or acceleration, and we looked at this one previously. The focus here is on these oscillations. So this is showing this ocean-generated signal, which has a period of about 6 seconds. You can see from peak to peak here, or roughly here from peak to peak, you can see about 5 or 6 seconds. This is viewing that signal in the time domain, where time is on the x-axis, and here velocity is on the y-axis. We showed previously we can also view these in the frequency domain, and this is showing the ambient noise spectrum for a station. Let's take the black one, Manly, shown here in black, and you see that for certain frequencies, it's largest. And if we look globally, as shown by these bounding spectra here below and above, everywhere in the world has this signal, and we can see that it's bounded. There's a peak right here at a frequency of about 0.2 hertz here, or a period of 5 seconds. And then there's this shoulder shown right here. And so globally, noise spectra show this weak peak right here and a stronger one at approximately twice the frequency. The first one is the actual period of ocean waves. The second one is caused by ocean waves interacting with each other, and that's the one that dominates globally seismic noise, even far from the ocean, such as Central Alaska. And so here's a picture of this station near Manly. It's on rock, pretty barren spot, and there is no ocean anywhere nearby. So it's kind of remarkable that wherever you are in the world, you pick up this signal from the ocean. I'm going to show a few results from a paper by Kyle Smith and myself. And this is showing the setting. Fairbanks is just off here to the east. This is Nenana. Here is Manly, the station we just looked at right here. The locator map shows we are in Central Alaska, just west of Fairbanks. And one of the key features here is this river, the Tanana River, that flows through Nenana, meets with the Nenana River, then flows north through this Minto Flats fault zone, and then to the west. And as part of our project, we deployed seismometers in this region and along the river. There's no roads and not even ways to land a helicopter in most of this area. Here's zooming in on the town of Nenana. It's at the confluence of the Nenana River and the Tanana River, population of 378. And it's also the location of weather and river monitoring instruments that we used in our study. So we'll see what the tripod is, a river gauge. Here's the landing strip here with a site at the airport to record weather. The tripod is a bit of an interesting side story. For over 100 years, local residents have erected a large wooden tripod on the river ice and then watched and waited and gambled on when breakup would occur, as indicated by this tripod falling into the river and moving a certain distance. So I'll give you an aside here and how this relates also to climatological data. Shows a newspaper from May 10th, 1923, when Nenana had a newspaper and was a big time there. If you look at this front page, we can see a lot of story about the breakup. It's talking about the ice pool grows $10,000 this year. The ice moves at Nenana. And here's the front page story starting at the bottom. Tanana ice moves, breakup starting. So it's not yet breakup here. May 10th, 1923, which is fairly late, as we'll see. 100 years later, this tripod is still providing valuable data. This shows all the data since then. It's actually archived at the NASA National Snow and Ice Data Center. And you can see what it shows is from 1917 all the way here to 2019. There's a lot of scatter of when breakup occurred. It's measured relative to the vernal equinox, March 21st. But what it shows is this downward trend tells us that the river ice is getting earlier. And it suggests the blue line that's about 8 days per century. So winter's getting shorter as measured by the ice going out. You also see this year was a huge excursion in 2019 to the earliest ever recorded breakup. And 100 years later, people are still gambling on the breakup time. You can see on the brochure for 2015, the jackpot was $360,000. So kind of an interesting Alaska tradition. We look at a few shots. This is from the live cam, March 9th, 2019. As I said, this turned out to be the earliest ever breakup. This is what the tripod looks like. You could screen capture this. So you get an idea of what this is about. This shows getting very close to breakup, the evening of breakup, 5:22 Alaska time. You can see that there's some water on top of the ice. The tripod is tipped, but hasn't gone the distance to be official. This shows that at 6:20, still not official, but then midnight that night was the earliest breakup ever recorded. And note the people, it's sort of a thing to do. It's come down and watch breakup happen. It's not usually that dramatic, but you can see in these photos, different people checking things out. So that's the tripod here. The meteorological data is recorded partly from a camera near the airport, and also across the landing strip is PANN, which is the meteorological data. You can get some sense of that from this tower shown, has cameras on the top. I'm now going to try to convey what a spectrogram is. We learned in the previous talk what a spectrum is, a way of looking at a seismic signal in the frequency domain, and we're going to now extend that to how those frequency signals vary in time. That's called a spectrogram. So we started looking at this, which was the ambient noise at station Manley. H was the horizontal component. Z was the vertical component. This is shown as the amplitude as a function of different frequencies for one station in black. We can tip this on its side. As you can see, it's shown here at left. We have the horizontal and the vertical component. When we tip it on the side, we can imagine that the size of this signal can get a different color depending on the amplitude. And that's shown in this plot. Imagine giving this high amplitude the greenish signal, and the lower values get the bluish signal. So we tip it on its side and we say, over all this period of time, let's just assume this was the average noise over that whole time period. The one at the top shows if in shorter intervals of time, like every day, we got a different spectrum, we could look at how this varied as a function of time. And that's what a spectrogram is. It's stacks of lots every single day, taking one of these spectra and then coloring it according to the amplitude. So you can imagine you're kind of looking down on these high ridges right here that go up and down based on the year. We can call this is the spectrogram. We can call B the average spectrogram, but then there's one other tool that's very convenient, which is to subtract B from A. And that gives us what's called a residual spectrogram, but it's basically a way of saying, I'm more interested in looking at the variation from the normal scene at this particular station or whatever it is. This is the typical scene. We're going to remove that from the spectrogram and look at the variability. And so that's useful as a monitoring tool. So spectrogram is a key tool for seismology in this time-dependent monitoring with noise. We can look back at this spectrum, and what we'll see, if I go back one, is we're interested to say if this is the background signal throughout, say, a 3 or 4 year period, we can ask the question, take MLY, for example, we can ask the question, how does it vary by season? And we can subset all these noise variations by season and look at the changes from this particular average signal. And so here's what it looks like for Manly. We've now subtracted out the overall average over time, and we're looking at deviations during different seasons. So if everything were flat here, it would mean that there is no variability from season to season. But what it shows, for example, in blue, it shows that this particular frequency band in the wintertime at Manly is higher, and in the summertime, it's lower. That turns out to be the ocean microseisms. And we can see here that for the lighter blue and the magenta, things are not as different. But we can use this as a tool to understand how things vary as a function of season or shorter time scales. So it turns out this spike is telling us that these ocean waves are strongest in the wintertime because they're coming from winter storms in the northern hemisphere, most likely the Gulf of Alaska. And during the summertime, there's still ocean-generated noise. It's just coming from winter storms in the southern hemisphere. And this spectacular, well-known fact now was highlighted in the previous slides here. But you can see as we break it down, even for a station like Manly, you can use it to understand these variations shown here. This signal from the oceans would be true across all of our stations. That's not the case for other signals. For example, here at Manly, on that treeless bluff rock outcrop, you can imagine it might be pretty windy. It turns out in the wintertime, the wind conditions are strong enough that the seismometer picks these up, and we'll look at wind later. So ambient noise at nearby stations can be very different due to local environmental conditions and also local structure, like the kind of geology below the station. So here's Manly, shown in black, and here's another station not too far away, F3TN, shown in black here. These are both with respect to the same red spectrum, which is sort of our reference station spectrum that's near the confluence of the Kantishna and Tanana rivers. But you see between the black here, Manly and F3, these are way different. This is higher across the board, just very noisy. Doesn't mean bad. It just means it's noisy for some reason. And that's what we'll look into. It's noisier here at these lower frequencies, and it's noisier at higher frequencies. So here we can look at F3TN and do the same thing where we say, well, how does things vary from one season to another at this station? Look at the deviations from the long-term average here and see what we find. So again, you find the high in the blue during the winter, low in the summer here. That's the long distance ocean generated signal. But then we have this huge signal varying strongest in the summer, much lower in the winter months, and also enhanced in the September, October, November. What we will see is this is the signal of the Tanana River, the flow of the river, which is quite close to this particular station. So we can look at a residual spectrogram, how things are changing relative to the background as a function of time. And we see here, so this is 5 years of continuous recordings at this station. And we can see this booming red and blue signal back and forth. And the vertical lines shown here are the dates of breakup as a dashed line and freeze up when the river freezes as a solid line. And we know those dates very well from the recordings at cameras in Nenana. We know them from cameras right at the site where we're watching the river. And so you can see that whatever this pattern is, it's strongly seasonal, and we could characterize it as saying it is large during the summer and lowest during the winter. This back and forth red, blue pattern that's sort of out of phase with this higher frequency signal is the overall ocean generated signal that every station in the world sees. This is not as interesting to us here. So you see higher frequency on the y-axis here, and we're looking at a line across 10 hertz. So there are seasonal changes in 10 hertz seismic signal at this station and 4 others, all of the ones that were on the river. And you can see here, if you look at the change in noise at 10 hertz as a function of time over this period of 5 years, you can see all showing the same thing, where there's some correspondence at 10 hertz. So there's some kind of regional pattern that is common to all of these. And this turns out to be the activity of the turbulence and sediment within the river. So the simple point is, this is the river gauge data at the town of Nenana. And you can see over the time, this is just showing the summer correlation. When the gauge height, when the water level goes up, the flow is higher. Usually goes up, peaks in summer and comes down. And these are colored by time of year. So red would be kind of the center of the summertime. Blues would be the margins of that, June and July, August period. And so you can see when these go up and get down, we also see the pattern with the seismic noise signal. So if we take one of these plots and plot it relative to the other one, so here on the y-axis is the seismic noise, and on the x-axis is the gauge height, we see a pretty nice correlation between river height and noise. When the gauge goes up, the seismic noise goes up as well. So that's giving us a very strong case that the seismic noise we're witnessing is related to the river. Before we get buried in seismograms and data, I just want to take us to the river itself. This is showing a photograph of the first trip. We went down 100 miles between Nenana and Manly to try to look for possible sites for seismic stations. This is Mike West, director of the Alaska Earthquake Center, Dr. Matt Gardine, Dr. Celso Alvazuri, myself, and we were doing this on the cheap, getting in the river. This is about the site where the tripod is, and also the measurement of the river gauging data that U.S. Geological Survey takes. This is the railroad bridge built in 1923 across the river. So it gives you some idea of the river. It is a wild river. If you're not from Alaska, this river would be a bit unusual. There's no dams, there's no control. It goes up, it goes down, it goes laterally. It's a difficult river to navigate, and it's somewhat difficult to do science on it. From Google Earth, here's a site where 2 of the stations were, F2 and F3. We've looked at F3 quite a bit. You can just get a sense for the meandering nature of this river when you look in Google Earth. It doesn't tell you anything about how much the water level goes up and down and how that impacts the navigable channels and so forth. But this gives you a picture of what this place is like. And to show a photo, this is taken from Old Minto along the Tanana River. It captures a few things. There's a lot of debris in the river, trees along the margins. You can see here, you can see the sand and the ripples. Just a reminder that these river systems are carrying sedimentation. And in terms of understanding why a seismometer picks up some kind of signal from the river, we have to think about what's in the river. It's water hitting itself, it's churning up sediments, depositing it. And so this captures some of that. Shifting to wind. So what is shown here is a spectrum during the winter from one station. This is F1TN. And you can say, show me the seismic noise when the wind nearby, as measured by something else, is very low. And that shows the black spectrum, no wind. And then you can, if you have wind data, you can take subsets of your seismic noise time and stack them up. And by each bin, you can say, show me what the spectrum looks like when the winds are 0 to 2 meters per second or 2 to 4. What you see is an extremely coherent picture, which is that as the wind gets higher for this station, the seismic noise gets higher. And keep in mind, the seismometer in the winter sits within frozen ground. Ground is frozen. You could not dig this up. You couldn't stick a pick into the ground. It's frozen solid. So it's strongly coupled to the earth. It's buried under snow. And so an academic question, is how is the wind reaching this? Well, we saw previously, these are extremely sensitive instruments. And this is one way that they are sensitive. They can pick up the action of the wind nearby on the ground, even at the level of 0 to 2 meters per second. In that category, you can see it's higher than if there's no wind. So that shows you how a seismic instrument is sensitive to wind. Shifting to another topic, glaciers and the discharge that comes out of glaciers. It's very important to think about liquids at the base of glaciers are between the glacier and its large-scale movement. So in the summertime, interested in monitoring that, this shows another spectrogram. Remember, frequency on the y-axis and time on the x-axis, and this shows the amount of power shown. And here they're interested in between 1 and 10 hertz looking at that signal. This is the Mendenhall Glacier shown here. There's a seismometer and also a gauge to measure the discharge. This shows a correlation between the seismic tremor signal in black and the discharge measured in blue. And hopefully you can see that when there are some very strong correlation between these two signals, again, similar to the river condition, only here looking at a glacier setting, there's a mechanism for using a seismometer to measure discharge, perhaps in places where, for example, you may not have that kind of instrument to measure, or maybe you already have a seismometer sitting out there. Let's put it to use doing some other monitoring. So it's a nice example of using seismic noise to understand glacier dynamics. Here's another example, is looking at seismic noise to monitor permafrost conditions. In this case, it's the 15 hertz noise recorded at Poker Flat. This is led by Stephanie James and others. This is showing a locator map for central Alaska. This shows a set of stations very close to each other in Poker Flat. You can see the scale bar is in up to 75 meters total. This shows location of Fairbanks right here. So this is just northeast of Fairbanks, 35 kilometers or so. That's the setting for this experiment. There's a lot of data shown here, but I'll walk through it. What is shown is air temperature on the top. You can see it's ranging from kind of grazing minus 40 Celsius or minus 40 Fahrenheit at the coldest conditions. You can see the soil temperature, different soil temperature measurements at different depths shown here. So when the air temperature goes up, you find the soil temperature is generally going up, but there's a delay between the temperature that slowly propagates deeper into the ground, as shown here. The bottom is showing the change in seismic velocity as a function of time over this experiment. So between the seismometer, they can use the noise to measure how fast waves travel between adjacent pairs. So faster areas means that the properties of the ground have changed. The fact that this is not constant means that the seismometers are seeing different properties, different mechanical properties in the ground. So let's focus on this. Here's two windows of time, February, March, April toward May. And as it says here, after the cold penetrates into the ground, the seismic waves travel faster. So here are the seismic waves traveling faster. Here's the air temperature, late winter, and here's the cold propagating into the ground. So a really nice example with these different instruments of showing that the properties of the seismic station is measuring mechanical properties in the ground. Colder temperatures makes it easier to transmit energy, and the wave speeds can move faster when this ground is solid, rather than in the summertime when it gets nice and warm and beautiful in Fairbanks. The ground warms up, it gets a little mushier, and the wave speeds slow down. Shifting out to the Bering Sea, the paper is entitled Quantifying the Influence of Sea Ice on Ocean Microseism Using Observations from the Bering Sea, Alaska by Sy and McNamara. You're seeing a locator map. Russia, Alaska. We'll be looking at 3 seismic stations: Tin City, Alaska, Gamble on St. Lawrence Island, and then UNV, Unalaska Valley, shown in the Aleutians. This map here, some of the data they use is sea ice concentration values identified from imagery, satellite imagery. And you can see here, this is Russia in white. It's a little bit odd. And this is TNA, so this is the western tip of the Seward Peninsula. This white region here would be the ice-free Bering Sea. So this is St. Lawrence Island, and this is Gamble. So some of the data will be looking at kind of calibrating seismic noise with known sea ice concentration. Here we are, spectrograms again, only this time is on the y-axis and it's period instead of frequency on the x-axis, but we're looking at how noise at these stations vary as a function of time at 3 places: UNV, TNA, and Gamble. And the arrows are pointing out these little notches where you see that the noise level drops, and you can see that this inference is due to is due to sea ice being present and noise levels dropping. So you can see these cases right here, and we'll explore these in detail in the next plot. So the blue shows the observed noise variations at periods between 0.6 and 2 seconds. And this is at Gamble, shown here. This is at TNA for 3 different time periods. And what is shown, the red, is the modeled noise based on the known sea ice extent, modifying the seismic noise at this nearby station in the Aleutians, UNV. And again, as shown earlier, the fact that these are following each other pretty nicely in terms of amplitude, and we can use the sea ice extent to predict the noise variations at these 2 stations, that suggests that you can use the changing noise conditions at these stations to thereby say something about the sea ice. And so the authors conclude saying it may be possible that using observed microseism variability to predict local mechanical strength of sea ice can be more accurate than using satellite observations of sea ice concentration to infer sea ice strength. Being able to predict sea ice mechanical strength, which is what a seismic wave is seeing, would be useful on a number of levels, including knowing how close the ice is to disintegrating. Such knowledge could potentially be useful for the shipping industry as well as climate scientists. So a nice example of using seismic noise for both practical and scientific levels, in this case with sea ice. So returning to the science fact about wind, rivers, permafrost, glaciers, sea ice, just a summary table to say, here was the conditions we were looking at in these examples. Here's the locations of each one. And then this is showing the study that we were mentioning. So 5 examples just showing how the exotic conditions in Alaska, coupled with some seismometers in key places, we can get better idea of how things are changing on local time scales and even longer ones. Takeaway topics: the Earth is continuously in motion. This continuous motion, or ambient noise, provides information on many things besides earthquakes. Seismic recordings can potentially be used for environmental monitoring while also picking up earthquakes and other signals. One of the questions is the seismometer the right tool for the measurement? Or maybe it's sitting out there already. So let's just opportunistically pick up some more information. Ambient noise is best characterized by spectrograms, which show how the strength of each frequency in a signal varies with time. For example, this 10 hertz signal of the Tanana River is highest in summer, lowest in winter, when the river is covered in ice. Thank you for watching. Please stick around for supplemental material.